Watch this video if you want to know how you can target 100% utilization ratios using evolutionary solvers in Grasshopper. Evolutionary solving using Grasshopper is simple if you want to either maximize or minimize your outcome. But what if you want to approach a certain value? In engineering and many other disciplines, utilization ratio is often a great performance indicator. You want to get as close to 100% as possible without crossing the line. Crossing the line would mean that something has more demand than capacity. Let's get to examples, and I will show you how you can target this using Galapagos or any other evolutionary solver in Grasshopper. Here is the example script. On the right, I have a representation of multiple floors with different areas that have different loads, load-bearing directions, spans, etc. My Grasshopper definition is trying to get each of these beams as close to 100% utilization ratio as possible by adjusting the beam section and the spacing of the beams. Now, it is not relevant if your use case isn't about construction. In Galapagos, we have option to minimize or maximize the fitness value. Now, if utilization is our performance indicator, we cannot use maximize directly because then it would be over 100%, and we cannot use minimize because it's gonna leave us underutilized. This is where a little Python script comes in handy. All you need to do is to penalize exceeding the 100% and then try to minimize 1 minus utilization. So in Python it looks like this. If the utilization is over 100%, our fitness value is going to be 1 plus utilization. And if it's less than or equal to 100%, then our fitness value is going to be 1 minus the utilization. So with real values, let's say we have a utilization ratio of 300%. It is going to calculate 1 plus 3 and output a fitness value of 4. And if our utilization ratio is, let's say, 90%, it's gonna calculate 1 minus 0.9 and give us a fitness value of 0.1. This is why we set Grasshopper to minimize, because then the closer the utilization is to 1, the smaller the outcome of this is going to be. It is clear that you need to penalize exceeding the utilization ratio of 100%, but I think that you shouldn't over-penalize it, because it's gonna make the fitness landscape so uneven that it's gonna be harder to find the peak values that are under the utilization limit. I'm gonna move this a bit and show you this in practice. Let's look at the first row. We have quite a large beam selection here. This is our utilization, and this is our fitness. If we start moving the slider in the gene pool that affects this first area, we see that as we go down, the utilization increases and the fitness value decreases. And as a reminder, we are trying to minimize, so smaller fitness value is better. Okay, so now our value suddenly jumped. This is because the utilization is now over 100%, and thus it gets penalized. I'm also using a color gradient here to display the utilizations on the beams. So low utilization is here, high utilization is here, and red means that it's over 100. Let's move the slider back a bit. Now we are at 95% utilization, and we get a really low fitness value, which is just what we want. I'm gonna draw a graph to illustrate this even further. Here we have a coordinate system with fitness and utilization as the axes. If we start from here, we move towards the 100% utilization, which is the best fitness. Then we penalize it by 100% if it crosses the 100% barrier. And then the values start slowly decreasing. Here is our target value. Now moving back to the script, I'm gonna open Galapagos, set this to minimize, and let the solver run. Okay, let's look at the results. We have an average fitness of 0.8, but for some reason we still have an area where the utilization ratio is over 100%. In this case, it's because I am using the section modulus of the beam sections in calculating the bending resistance, and I have just listed some section dimensions, and because the resistances are not sorted, the genetic solver gets stuck in a ridge because the next value is not better than the one that we currently have. To better explain this, we have different values like this for our bending resistance. Our best value is here that we got from the analysis. The actual best value would be somewhere there. And if we're trying to check close to this, we have arrived at a local optima because both of these values are still worse than this one. This is a common pitfall in genetic algorithms, so please keep this in mind. If you get stuck like this, you can manually help the algorithm a little bit until you arrive at the better solution, and then continue with the solver. I'm gonna stop this here because we have already reached much better results than what we had before. If you have any questions regarding this, or you have a video idea that you want to learn more about, don't hesitate to drop a comment. That's all for now. If you learned something, hit the like button and subscribe to the channel. I'll see you in the next